Hello, I'm Charlie, and I'm going to be talking about how we can improve the sensitivity of Hyper-K to CP violation in neutrinos through the use of new near detector measurements. So a brief overview of the topics. We'll cover the motivation for measuring delta CP at Hyper-K, why electron neutrino and antineutrino cross-section knowledge will be critical for this measurement, the new near detector that we intend to measure these electron neutrino cross-sections with, the IWCD, and our strategy for doing so. And then finally, the results of the cross-section study and the impact on the sensitivity of Hyper-K. So first, Hyper-K has a wide range of physics goals, ranging from proton decay to atmospheric neutrinos. But one of the core components of the project is the long baseline program. This builds upon the successful method employed by the T2K experiment of using an accelerator-based neutrino beam, a suite of near detectors, and a far detector. And this will be especially sensitive to delta CP. The results of T2K already show that there's a 2 sigma preference for CP violation in neutrinos. However, due to the limited statistics of T2K, these results here come from approximately 100 signal events. T2K itself will never gain the statistics necessary for a 5 sigma result, and so we will require a leap in event rate. And that's what Hyper-K can provide. This will use a detector of similar Water-Cherenkov design to Super K, but with 8 times greater mass. We'll be coupling that with an increase in the power of the neutrino beam, moving from half a megawatt to 1.3 megawatts, and these two combined will allow Hyper-K to move from the order hundreds of events that we see at T2K to order thousands with Hyper-K. So here you can see the distribution of electron neutrino and antineutrino signal events at Hyper-K after 10 years of running, and the available statistics we'll have. And for more on Hyper-K itself, please see the talk from Jian that goes into the construction and other physics goals. So next, how do we actually measure delta CP at Hyper-K? Well, we'll be sensitive to it by looking at the oscillation of muon neutrinos into electron neutrinos and their antineutrino counterparts. The impact of CP violation is to change the relative appearance rates of electron and anti-electron neutrinos. So for example, here we can see the difference between CP conservation case for electrons and for anti-electron neutrinos. So for example, if delta CP is negative, then we expect the electron neutrino event rate to increase and the anti-electron neutrino event rate to decrease. So the ratio of the electron neutrino to antineutrino encodes the delta CP information. So one important impact of this is that any systematic uncertainties that affect this expected ratio will have a direct effect on our delta CP sensitivity. So here you can see the ability of Hyper-K to exclude CP conservation for a range of the true values of delta CP, and with 2 different systematic assumptions. So in our current uncertainty in blue from T2K, and what we hope to be able to achieve with Hyper-K in red. And you can see this has quite a significant impact on our ability to exclude values. And it turns out that the major systematic that's at play here is the electron neutrino and antineutrino cross-section, which is not currently well constrained by experiment. So for Hyper-K, we will need to measure this ourselves. And that's one of the major goals of our new near detector, the intermediate Water-Cherenkov detector. This is a cylindrical Water-Cherenkov detector with an inner detector massing approximately 300 tons and is placed approximately a kilometre from the neutrino production point. The detector itself sits within a vertical shaft and can be moved up and down to scan the angular profile of the neutrino beam, and in so doing measure the different fluxes that are present within, but more on that later. The detector itself is instrumented with these multi-PMT assemblies, which are composed of many smaller individual PMTs. And this allows for high granularity in a small detector, which is essential for accurate reconstruction. The aim for the IWCD is to start collecting data from the very beginning of Hyper-K and continue throughout the run. And so for more details on the IWCD itself, please see Patrick's talk on this. So as an electron neutrino cross-section apparatus, the IWCD has a number of advantages and some disadvantages. One disadvantage is that due to the Water-Cherenkov reconstruction, we have no charge selection and therefore can't distinguish neutrino from antineutrino events. So to make neutrino and antineutrino samples, we must rely on the operation mode of the neutrino beam. However, there are a number of advantages. The very large mass of the detector allows for even the very small electron-neutrino component of the beam to yield order tens of thousands of events, and this is essential for making a precise electron-neutrino cross-section measurement. In addition, the detector can move within its vertical shaft, and so be placed at different angles away from the central axis of the beam. Due to the angular dependence of the decays that produce the neutrinos, the different regions away from the center of the neutrino beam have very different energy distributions of the neutrinos. So you can see here the muon neutrino flux decreases in energy as we move further from the center of the beam and decreases in overall intensity. For the electron neutrino measurement in particular, this is useful as the positions further from the center of the neutrino beam have a greater proportion of electron neutrino flux compared to areas closer to the center. So here you can see the ratio of electron to muon flux in the beam, which increases from 0.8% at our position closest to the center of the beam to up to 1.4% as we move to our furthest position away from the center. And this allows for the creation of more pure electron-like samples in these regions further from the center and therefore a more precise cross-section measurement. So with that in mind, we need some method for extracting these cross-sections. To do that, we can use a model-dependent fitting approach very similar to that currently used by T2K for their near detector ND280. This involves the use of a neutrino interaction model, which is constrained by theory and by external data. We then have a model of our neutrino flux, which is likewise constrained by external data and our beam monitoring information. Then we have detector uncertainties, such as the uncertainty on the energy reconstruction and interaction pileup, which I'll get onto later on. And then finally, we have the samples from the IWCD, which can be used to constrain the parameters present in all of these models. At the end of this process, we can extract a constraint on the electron-neutrino and antineutrino cross-section in a form that can be applied to the FAR detector. We therefore need a number of samples to do this with. First, we'll need to constrain the charge current neutrino interaction model. We can do that through the use of a charge current muon and charge current muon anti-neutrino sample. Here we'll have an extremely large number of events, order 1 million or so signal events available. And this will allow us to really tightly constrain this portion of our model and therefore get a good constraint on the interaction model. Next, it's necessary to constrain the neutral current component of the cross-section model. Here, neutral current events, especially pi0 events, are a major background for our electron samples, and so we must constrain these very well. And again, we have a large neutral current sample to do that with. And then finally, to measure electron-neutrino cross-sections and antineutrino, we need selections of electron-neutrinos and antineutrinos. Here, the major challenge is in rejecting neutral current backgrounds, especially pi0 events. But overall, we're able to achieve a quite pure sample, especially given the very small available electron-neutrino flux in the beam. And these all correspond to 10 years of data collection and are the neutrino mode samples. There are equivalent antineutrino mode samples as well. We then also have detector systematics to consider. For one, the IWCD will face a challenge with interaction pileup. We have a quite large detector in an extremely intense neutrino beam, and so there is a chance that multiple neutrinos will interact within the detector in a single beam bunch. Reconstructing events in this pileup environment is challenging, especially if the rings of these particles overlap in our detector. It'll be very difficult to reconstruct. And so we expect that a large fraction of these events will not, in fact, be reconstructible. Since the probability for multiple interactions depends upon the neutrino flux, there's a strong dependence of off-axis angle on the pileup. So, for example, at closest to the center of the neutrino beam, where the flux is highest, only a small proportion of events we expect to be reconstructible, whereas further away from the center of the beam, the flux is lower, and so a greater proportion can be reconstructed. We intend to measure this pileup, however, it will have some uncertainty in the fit. We then also have uncertainty on the energy reconstruction for muons and for electrons separately. And finally, our goal is to gain a useful constraint for the far detector. Since we expect nuclear effects and radiative corrections to impact electron and muon neutrino events differently, we can't simply use our muon neutrino cross-section as our electron neutrino cross-section. And so we need to parameterize the difference between electron and muon, and likewise for antineutrino. If we were to use a single parameter to control this difference, this would be insufficient, as we expect that the difference will be a function of instant neutrino energy. And as you can see, the flux that we measure at our near detector is very different from the oscillated flux that we measure at our far detector. If we were to have a single parameter, then this high energy tail of our IWCD sample would constrain the cross-section in the area that we're actually interested in around the oscillation peak at around 600 MeV. So the solution is to make a measurement as a function of instant neutrino energy. So we take our electron neutrino sample and our antineutrino samples, we split these into several different regions and assign a separate independent normalization parameter to each region. We're especially interested in the constraint offered around this flux peak at around 600 MeV, and as you can see, we have a large enough sample here to expect good results. So if we take all these considerations and include them in the fit, we can have a look at just the resulting electron neutrino and antineutrino constraint. So you can see that around the region of interest, around 600 MeV, we're able to constrain the electron neutrino cross-section down to the sub 5% level. And for the antineutrino, we do slightly worse, constraining to about the 8% level. The reduced constraint on the antineutrino is due to the increased contamination present in this sample. We have a large background of electron neutrino events in our electron antineutrino sample. And this limits the power of this sample to constrain the antineutrino cross-section. In addition, we have some relatively strong positive correlations between the electron neutrino and antineutrino parameters, and this acts to reduce the uncertainty in the ratio of the two, which is ultimately what affects CP sensitivity. So this is helpful. So if we take these parameterized cross-sections and apply them to the signal event distribution at our far detector, we can look at the resulting uncertainties in the event rates as a result of this cross-section uncertainty. So here we have the uncertainty on the ratio of the number of electron events to the number of electron antineutrino events at Hyper-K, with the theoretical only constraint giving us an error of about 4.9% on this ratio. Using the results of the IWCD, we can reduce this down to about the 3.7% level, so a significant improvement. Next, if we take this IWCD constraint and use it in a Hyper-K oscillation fitting framework, then we can investigate the impact on CP sensitivity. And that's what we can see in this plot. So this new purple dashed line is our sensitivity with this IWCD energy dependent cross-section. And you can see that we're able to do slightly better than the theory-only single parameter constraint in blue, but we're still a bit of a distance away from our goal uncertainty for Hyper-K in red. Nonetheless, with this IWCD constraint, we're still able to exclude more than 50% of true delta CP values at greater than 5 sigma and more than 70% at 3 sigma. Another thing this indicates is that any additional improvement in the IWCD constraint will have a significant positive impact on the overall Hyper-K sensitivity, and that's the subject of ongoing studies looking into the design of the detector and improved fitting methods. So in conclusion, we've looked at the ability of the IWCD to constrain electron neutrino and antineutrino cross-sections. With it, we're able to achieve a sub 4% uncertainty at the far detector, and additional work is ongoing to improve this even further. And then finally, the IWCD and indeed Hyper-K as a whole offers the potential for this type of measurement and other new high statistics neutrino measurements not previously possible. And so new collaborators are very welcome to join. If anyone has any questions, I'll be very happy to answer them in the neutrinos panel. Thank you very much.